Here I'm going to solve some of the problems on biasing of the transistor, mainly focusing on the fixed bias and the self-bias circuits. We'll also see some of the problems wherein how does the variation in beta affects the collector current, the base current, etc. These are the problems we are going to solve in this particular set of slides. You may try solving it yourself before moving on to the solution. The part A of first problem, it states that for a fixed bias circuit that uses the silicon transistor, the base resistance RB is 500 kilo ohms, RC, the collector resistance is 2 kilo ohm, the supply voltage VCC is 15 volts, ICBO, the collector leakage current is 20 microamperes, and beta is 70. We have to find out the value of IC and VCE at the Q point. We can assume the value of VBE to be equal to 0.7 volts. It may not always be specified the value of VBE. The moment it has been specified that the silicon transistor, we can also assume the value of VBE equal to 0.6 or 0.7 volts. So this is the circuit, the fixed bias circuit, wherein we have been given with RB, RC, VCC. The beta value is given and VBE is also given. We have to find out what is the collector current and we have to find out what is VCE, for which we may have to find out IB first. So these are the given parameters. So first we need to find out the value of IB. IB is nothing but VCC minus VBE, that is VCC minus VBE divided by RB. That gives us the value of IB. So the substitution of all the parameters which have already been given gives us the value of the base current to be 28.6 microamperes. Since the value of ICBO is given, the collector leakage current is given, we will have to substitute also for ICBO in the expression when we find out IC. So if ICBO is not given, the collector current will simply be beta times IB. But since we have been given with ICBO, the collector current expression will be beta IB plus 1 plus beta into ICBO. Now this particular component is also equal to ICEO. ICEO is equal to 1 plus beta into ICBO. And we substitute the value of beta IB and beta again here and ICBO. That gives us the value of collector current to be 3.422 milliamperes. And finally we have to also find out VCE, the collector to emitter voltage, which is nothing but VCC minus ICRC. The substitution gives us the value of VCE to be 8.156 volts. Having found the value of IB, IC and VCE, we can plot in the output characteristic where exactly the operating point lies. A minor modification in the previous problem, we have to consider all the parameters as same, but the only change is beta changes from 70 to 100. Now how is this value of beta going to affect the base current, the collector current and VCE? That's what we have to see. We can also see if it affects the variation in the Q point. So these are the given parameters and the circuit is this. So again we have to find out the value of IB. Here IB is not getting affected by beta, so we have the substitution gives us the value of IB same as the earlier one, 28.6 microamperes. But here comes the change, the value of beta has to be substituted when we calculate IC. So when we do so, we see that the value of IC changes to 4.88 milliamperes. If you remember in the earlier problem, for beta is equal to 70, we had the value of IC to be 3.244 milliamperes. Now a variation in beta has affected the collector current. Similarly, VCE, when we calculate, the value of VCE has changed from 8.125 to 5.24. So that's how the variation in beta has affected the Q point. Q point will obviously now getting shifted towards the saturation region just by the change of beta, keeping all other parameters same, VCC, RB, RC, everything has remained same, but if the transistor has been replaced by a transistor which has a different beta, this is how it is going to affect the Q point. So comparing the results of 1A and 1B, the problems 1A and 1B, earlier we had in the first problem we had obtained for beta is equal to 70, VCE was 8.156 volts. Corresponding to that, the output current, the collector current, was 3.422 milliamperes. And when beta changed from 70 to 100, the VCE value changed from 8.156 to 5.24 volts. Correspondingly, the collector current was 4.88 milliamperes. Now we see that the Q point, which was in the center of the active region, has now shifted toward the saturation region. So further variation in beta would tend to move the Q point towards the saturation region, thereby distorting the output if you are making use of the transistor as an amplifier. The second problem states that a silicon transistor is biased for constant base current. That means it is biased for in a fixed bias circuit, making use of the fixed bias circuit. If beta is 80 and VCE is, which is already given as 8 volts, RC is 3 kilo ohm, VCC is 15 volts. We have to find out ICQ and also the value of RB, which has not been given in the problem. The problem has to be repeated if the transistor gets replaced by a germanium device. So the circuit of the fixed bias, and these are the given parameters. We have to find out IC and RB. So we have the expression for VCE. We have to first make use of the expression of VCE, thereby we can find out what is the value of IC here. We have been given with VCE already, VCC is given, RC is also given, so we can find out the value of IC making use of the formula, and the substitution gives us the value of IC to be 2.33 milliamperes. So since the value of ICBO is not given, we can straight away find out the value of IB. The relationship between IB and IC is IC is equal to beta times IB. So therefore IB is IC by beta. So that gives us, given the value of beta to be 80, so we have IB is equal to 29.16 microamperes. And having found IB, we have the expression for IB, which is equal to VCC minus VBE by RB. So making use of the same formula, just reformulating it, we'll have RB is equal to VCC minus VBE by IB. So that is, this resistance is equal to the voltage across the resistance, that is VCC minus VBE by the current IB. So IB we have already found. So substitution of that is going to give us the value of RB to be equal to 490 kilo ohm. So in the second part of the problem, where we have to replace the silicon transistor by a germanium transistor, we can actually consider all the parameters to be same. That is, IC is 2.33 milliamperes, IB is 29.16 microamperes. Considering all the parameters same, we can simply determine the value of RB. So how is it going to affect the value of RB is, here VBE will change from 0.7 volts, earlier it was, to 0.3 volts. So under such case, the calculation will lead us to a value of RB to be equal to 504.1 kilo ohm. So if we make use of this particular resistance, the base resistance, all these parameters are going to remain the same. That is, IB will remain at 29.16 microamperes and IC will remain at 2.33 milliamperes. This is a similar problem as we have solved in the earlier case, the second problem. We are given with VCC, RC is given. Given that the transistor is germanium, beta is 50, ICEO is 0, and VCE saturation is 0.2 volts. We have to find out the value of RB. So this is the circuit, and these are the given parameters. The only difference is that the VCE The value of VCE earlier was not the saturation value, but here in this case, the VCE is given that it is the saturation value, which is equal to zero point 0.2 volts. So that obviously is going to give us the corresponding saturation collector current. So IC sat will be VCC minus VCE saturation by RC. So it must give us a high collector current, which is nothing but the saturation current, when VCE saturation is zero point 0.2 volts. If the saturation voltage of VCE is not specified as zero point 0.2 volts, we can assume VCE saturation to be equal to 0 volts. That's fine, because when the switch, ideally when the switch is on, the voltage across the switch is 0. Here we have a very low voltage, so ideally we can say that VCE saturation is equal to 0 volts. So having found that, we are going to also get the value of IB. This is going to lead us to a value of IB which is equal to 74 microamperes. And similarly, we also have to find out RB, which is VCC minus VBE by RB. Substitution gives us the RB value as 198.64 kilo ohms. Now, if we make use of the transistor with all these parameters, the transistor will be in the saturation region. We can make use of the transistor rather as a switch, where it will be conducting the current with a zero resistance across the collector and emitter. So those were the few of the problems with respect to fixed bias. Now let's solve problems on the self-bias circuit. Stating the first problem, for a self-bias circuit, the transistor is a silicon device. Given that Re is 200 ohm, R1 equal to 10 R2 is equal to 10 kilo ohm, RC is 2 kilo ohm, beta is 100, and VCC is 15 volts. We simply have to find out IC and VCE. Is a straightforward problem where the given circuit is a self-bias circuit, where we have R1, R2 which are already given, RC is specified, RE is also specified, and VCC is 15 volts. The value of beta for the transistor is 100. We have to find out IB first and IC and then IE. In case of the self-bias circuit, we know that the circuit has to be replaced with its equivalent, the Thevenin's equivalent, where we have to calculate the RTH value, which is R1 and R2, which are in parallel, comes out to be 909.09 ohms. We also have to find out VTH, which is VCC R2 by R1 plus R2. So that gives us VTH is equal to 1.3636 volts. From this, we can find out the value of IB, which is VTH minus VBE upon RTH plus 1 plus beta into RE. The substitution of all these values, wherein we have found VTH and RTH has been found, VBE, if it is not given, we can assume it to be 0.7 volts, and RE and beta are given. The substitution gives us the value of IB to be 31.435 microamperes. Similarly, IC is just the multiplication of beta and IB, which has been found, gives us IC value to be 3.1435 milliamperes. And VCE is VCC minus IC into RC plus RE, gives us a value of VCE to be 8.0843 volts. A little modification in the earlier problem, where earlier we had the value of beta equal to 100, and now in this particular problem we are going to change the value of beta to be 75, and let's see how it is going to affect IC and VCE. So given the circuit, the self-bias circuit, given all the parameters, the same parameters, and the beta now it is going to be 75. We have to first find out RTH, which are R1 and R2 are in parallel, and VTH, the Thevenin's voltage, comes out to be the same. First, when we find IB, here we have the same formula, but beta is what changes here. Now the variation in beta is going to affect IB. Earlier we had the value of IB to be 31.435 microamperes. Now it has changed to 41.194 microamperes. So there is a drastic change in the value of IB, or the input or the base current. Now when we find out the collector current, which is IC is equal to beta times IB, So substitution of new value of beta, see that the collector current is now going to be 3.089 milliamperes. The earlier value of collector current was 3.1435 milliamperes. Here we see that there is only a minute change in the collector current when it comes to the self bias circuit. Earlier, when we had solved one of the problem on fixed bias, we saw that the change in beta value has changed the collector current to be a large value. But now there is only a minor change in the collector current. Similarly, let us also find out the VCE. That comes out to be 8.202 volts. The earlier case when beta was 100, we had the value of VCE to be 8.084 volts. Even there is only a minute change in the VCE, the collector emitter voltage, even though the beta has changed from 100 to 75. Now this is the advantage of self bias circuit, wherein the variation in beta is not going to affect the Q point. It is not going to vary the output current, whereas the also the output voltage. Going through the fifth problem, for a cell bias circuit which uses the silicon transistor, given that Re is 300 ohm, Rc is 500 ohm, Vcc is given as 15 volts, beta is 100. If 10 R2 is equal to beta times Re, then determine the value of R1 to get a VCE which is equal to VCC by 2. So these are the given parameters we have been given with the emitter resistance, collector resistance, the supply voltage is 15 volts, beta is specified. From this given formula we can find out what R2 is, and VCE is VCC by 2, that is going to be equal to 7.5. Since VCC is 15 by 2, VCE is going to be equal to 7.5 volts. So we have to finally find out R1. The only unknown here in this problem is R1. Since we have been given with all the output parameters, so we can make use of the output expression first in order to get some of the output parameters. So in here we have been given with VCE, VCC is given, RC and RE both are given. We just have to find out IC. So just reformulate to get IC and substitute. That is going to give us the value of IC to be 9.375 milliamperes. So once we have found that, we can also find out IB. The ratio of IC and beta is going to give us the value of IB. We know the expression for IB when we apply KVL across the input loop of the self bias circuit. We get the expression of IB to be VTH minus VBE upon RTH plus 1 plus beta into RE, where RTH is R1 R2 by R1 plus R2, where we know what is R2 because it is given that 10 R2 is beta times Re, where beta is 100 and Re is 300 ohms. Substitution of beta and Re is going to give us the value of R2 to be equal to 3K. So we get RTH is equal to R1 3K upon R1 plus 3K. Similarly, so that's what we can substitute here in RTH, and we also need to know what VTH is here, so which is VCC R2 by R1 plus R2. So VCC into 3K upon R1 plus 3K. So now in this expression we can substitute for VTH, we can substitute for RTH, and VBE we can assume it to be 0.7 volts, and beta we know, Re we know. So the only unknown in this expression is R1. We also have found out what IB is. We have to substitute for VTH. We substitute also for RTH here, and rearranging we are going to get the value of R1 to be 8.796 kilo ohms.